Hi guys, in this session we're gonna reach to conservation of mechanical energy. However, before we do that, we have a couple of things that we need to agree on. So let's get started. So the first thing we're gonna start with is internal energy. So we have studied mechanical energy, which is the macroscopic energy. Now we move to internal energy. Internal energy is the sum of kinetic and potential energies of particles within the system. That means whatever you can think about concerning atoms, molecules, and particles inside a certain object, all their energies form what we call internal energy. Now, to exchange that internal energy, we refer to something that we define as heat or thermal energy. Now, the exchange of internal energy with the surrounding might be some vibrational energy or some other forms. However, by default, we assume that any energy lost from the internal part of the object is lost as heat. Okay? Now, in order for heat to be exchanged, in order for internal energy to be lost, we need a specific type of forces, these forces that are able to interact with the object from within. Such a force is called non-conservative force. An example of these forces is friction or traction force. For example, friction allows particles from a certain object to interact with particles of the surface of a solid where that object moves. Okay, that's why this type of force allows internal energy to be lost. Now, mathematically speaking, you can calculate heat or the internal energy lost by an object by simply calculating the work of the forces that are non-conservative, such as friction. Once you do that, in mathematics, we say that heat equals minus the work of these forces. Why minus? Simply because the heat of an object is due to the work done by these forces and lost to the surroundings. Now, after defining internal energy, we can go to total energy, which is simply the sum of both internal and external energy. External energy is what we refer to as mechanical energy. There's a main concept that we can never violate, which is energy is neither created nor destroyed. It is always, always conserved. That means if mechanical energy increases, internal energy must decrease and vice versa. Let's take these examples. When the brakes are applied, friction acts on the wheels, thus slowing down the car. This means that mechanical energy is going to decrease. And as mechanical energy decreases, the internal energy of the car increases. That's why the wheels heat up. Or if you touch the cylinders of the wheels, you will notice that they are extremely warm. That means that the mechanical energy lost was increased as internal energy of the object. That, by the way, explains this equation. Delta ME equals minus delta U. The variation of mechanical energy is opposite to the variation of internal energy. If the first one decreases, the second one should increase and vice versa. Another example is when a rocket is launched. When a rocket is launched, internal energy, which is chemical over here, is lost, so it decreases. As a result, mechanical energy increases and the rocket launches and moves up. So these are simple examples of the exchange of mechanical energy into and internal energy. Now, the important part that we as 12th graders should focus on is the conservation of mechanical energy. We said that the variation of mechanical energy is opposite to the variation of internal energy. So now think about it like that. If internal energy is preserved, nothing is added to that internal energy, and nothing is taken out of that internal energy, then it's going to be conserved. As a result, mechanical energy is also conserved. This concept is known as the conservation of mechanical energy. And in the case of internal energy being preserved and isolated from all the surroundings, we say that the system is energetically isolated. As you can read here, a system is said to be isolated or energetically isolated, to be more specific, when frictional forces, chemical or nuclear reactions are absent. Once these conditions are met, we can say that mechanical energy is conserved. Take a look at the figure that you can see to the right side. You notice that there's a man carrying a stone and lifting it above ground. At that instant, the system, stone, man, and earth possess all energy as gravitational potential. Now, when the man releases the stone is halfway or somewhere in between the highest point and the ground. The system, stone, earth, and man, if you want to say, possesses two types of energy, gravitational potential energy and kinetic energy. Together, they form mechanical energy. And the important thing is that the sum of GPE and KE at this point is equal to the gravitational potential energy at the beginning. Now, the final position when the stone hits the ground has no height, so it has no gravitational potential energy. We're taking the ground as reference, then all energy is converted into kinetic energy. Again, this concept is the conservation of mechanical energy. Now, if you link mechanical energy and the concept of conservation of mechanical energy to the total energy, linking to total energy conservation, delta E total equals 0. Here we're dealing with mathematics. Or delta ME equals minus delta U. In an energetically isolated system, there are no non-conservative forces, the forces which allow the change of internal energy, such as friction or traction force. Thus, delta U, which equals summation of work of non-conservative forces, equals to 0. Notice the mathematical flow here, okay? Thus, notice we said here, delta ME equals minus delta U. Now, delta U is summation of work of non-conservative, as you have seen in the previous slide. When this is 0, then delta ME becomes 0. Hence, mechanical energy is conserved. Now, let's move to an application which focuses on this point, on the idea of conservation of mechanical energy. This application is simple. It has some calculations, but using it or solving it, we're going to get used to the way of solving problems with mechanical energy. So a box of mass m, 100 grams, starts from rest from point A. It slides on a frictionless ramp, where there is no friction, inclined at an angle of 30 degrees with the horizontal. A free spring is placed at the bottom of the ramp, such that its free extremity is at point O, as you can see in the figure. Now, we consider the horizontal line passing through O to be the reference of gravitational potential energy, which we denote by GPE0. GPE0 means the reference. Knowing that OA is 60 centimeters and the spring stiffness is 80, determine using the principle of conservation of mechanical energy of the system, Earth, S and R, the distance OB, where B is the point where S stops. Now, you will not find the solution here. We're going to talk about the solution later on in another section or another session. Nevertheless, I want you, anyone who is watching this video, to try to solve this on your own. Do mistakes, it's fine. Before you watch the following video, try to solve this and have some mistakes so that once you watch over the solution, you will get used to how to solve such types of problems. Another exercise which can be solved as homework after you watch the solution of the previous application in the following video. We have a simple pendulum which is composed of a ball of mass m and an extensible string of length 2.3 meters. You can see that in the figure. P is shifted by 30 degrees from the vertical and then it's shot with an initial speed of 4 meters per second. The pendulum rotates until it reaches a maximum elevation at point E on the other side with the vertical. Friction is neglected. Calculate the mechanical energy of the system, determine theta max, calculate the speed of m as it passes through the equilibrium position, and then deduce the value of the tension in the string. This might be a bit challenging at this level of the course. At what angle are the kinetic energy and gravitational potential energy of this pendulum equal? Part 4 is a smart question. It's not hard, but thinking about the solution might be challenging. Now, this is a nice application. If you are able to solve this exercise, that means we are ready to finish and end up this chapter. Okay? Those who find this easy, you can go to the official book of the Lebanese official or curriculum and go to page 25, give or take, and solve exercises 8, 10, and 14. In the upcoming section or session, we're gonna solve the application, then we're gonna add quick solutions of this exercise and the assigned exercises from the official book of the Lebanese curriculum. That's all concerning this session. I hope that you got the idea of conservation of mechanical energy. Before we leave, I would like to take a look at this picture here, and if any one of you practices archery, I think you have used the ideas of mechanical energy somewhere. When you pull the bow back, you are producing some potential energy within the system of the arrow and the bow. Then, once it is released, that energy is going to be converted into kinetic energy. So this is just an idea about using mechanical energy in one of the sports that we do in our daily life. Anyway, just focus mathematically on the conservation of mechanical energy. Try to relate it conceptually to the conservation of total energy, and by this we'll have covered everything concerning the important parts of mechanical energy lesson. Until we meet again, take deep care of yourselves and thank you for your time.